Okay, so we're talking about the fundamental nature of stuff today, matter and volume and energy and all of that. When we talk about matter, an object, something that is real, it has some kind of mass, some kind of weight to it. You can pick up something and say, yeah, there's something to that. I can feel that. Even very, very light things have mass in some real way. And so anything that is matter has mass and volume. It takes up space. Okay, this roll of tape takes up less space than I do. I take up less space than I did last year. But there's some object, if it's a real object, it has mass, it has weight to it, and it takes up space. Okay, it has volume. When we talk about stuff, matter, there's a couple of vocabulary words we need to have, and you had these back in physical science. As a matter of fact, I gave this exact same lecture to physical science today, at least this slide of it. And so I know that you've had this before because Mr. Long, I'm sure, did a great job with you in physical science as well. So when you take something, anything, this roll of tape, and you cut it in half, you have two parts of that thing. And they're still the thing. It's just half of it, right? And you keep cutting it in half, and keep cutting it in half, and keep cutting it in half. And eventually you get down to something that is so small that if you were to cut it in half again, it would stop being that thing. It would start being something else. So in some cases, we're talking about an atom, and in some places, we're talking about a molecule. So if you have a pure substance like gold, if anybody has a 24-karat gold ring or 24-karat gold necklace, it's pure gold. You cut that thing in half, which you wouldn't do because it's valuable and it's a piece of jewelry, but just pretend. You cut your gold ring, your 24-karat gold ring in half, and now you still have gold. You cut it in half again, you still have gold. You keep cutting it in half, eventually you need very small saws, and then maybe you need lasers. And at some point you get down to a gold atom. That's the smallest thing that you can have that's still gold. It still has the properties of gold, it still behaves like gold, it's still gold. But if you take a gold atom and cut it in half, now you don't have gold anymore. You've got whatever half the atomic number of gold is, okay? So a pure substance we call an element. And the smallest functional unit of that pure substance is an atom. And an atom is the smallest thing that behaves like the element that it belongs to. Similarly, if you have a substance that is not a pure product, like a pure element, if it's not just gold or copper or silver, if it's something like my ring is made out of, which is stainless steel. So this is actually carbon and iron that are mixed together in a certain way to make stainless steel. If you cut this in half, you still have stainless steel. Cut it in half again, you still have stainless steel. Cut it in half a whole bunch of times, and eventually you get down to something called a molecule, which are actually multiple atoms joined together to make a thing. And the molecule of stainless steel is the smallest molecule that will behave like stainless steel. If you were to cut it again and knock off some of the carbons off of the iron, you would no longer have stainless steel. You would have carbon, which is a black, brittle substance, and iron, which is not, right? And neither of those are stainless steel. And so the idea here is a compound is a substance that is not pure, that's got different things in it. And they're arranged in a certain way where the smallest unit of that is a molecule. And molecules are the smallest part of a compound that still behaves like itself. And an atom is the smallest part of an element that still behaves like itself. So let's, I think I have one more slide before some pictures. Yes, in truth, I do know I have pictures. There you go. Atoms. So you saw these pictures before back in physical science. An atom is made up of other things inside of it. We'll get to that. For right now, it's an atom, okay? Protons and neutrons and electrons. And this is the smallest thing that behaves like carbon. If you have not all of this, you don't have carbon. It's something else, okay? But if you take a bunch of atoms and you mix them together, you get molecules. This is another picture of an atom, and I just put these here to help us understand again and reinforce what we talked about last week, that science sometimes changes, models improve and change and get more workable and reliable over time, but the Word of God does not. So the Word of God that was written back in the 1600s when this concept of an atom was being first kicked around was, the Word of God was the same, but our understanding of the atom was this. And now, over time, it's gotten more complex, and it's gotten more complex, and it's gotten more complex. And now when we picture atoms, we talk about stuff like this, which is just weird. Looks like a game piece. But this is more what an atom probably looks like, if you could see it. Models change, the Word of God does not. However you want to draw it, an atom is the smallest piece of something that behaves like itself, okay? The smallest piece of an element. You take multiple atoms and you stick them together and you get a molecule. And this happens to be water, right? 2 hydrogens and an oxygen joined together. You are 70-something% that. And this water has certain characteristics that are not the characteristics of oxygen, not the characteristics of hydrogen. It's the characteristic of what you get when you put these things together. So if you take a drop of water and you very carefully, move it into 2 piles and move those into 2 piles and those into 2 piles, and eventually you're using, lasers and magnets and crazy things to try to move it around, you might eventually get to 1 molecule of water. Probably not, but you could, in theory, get down to 1 molecule of water. And when you get there, that's the smallest thing that will behave like water. If you were to cut this in any place, you would not have water. Okay, and molecules can get more complex. This is a fairly simple organic molecule, but you can see lots of atoms involved and lots of different bonds and different kinds of bonds. You'll meet these guys later. And it gets more and more complex to, I should have a picture of DNA. No, it didn't load. Anyway, some molecules are very, very, very big, and they are quite complicated. Okay? So atoms are the simplest unit of an element. Molecules are the simplest unit of a compound. And there's lots of those things out there. If you look at the periodic table, there are right around 100 elements that are real and findable, and labs are making more and more of them that don't actually exist, at least in our planet. But we've got all these things out there. How do we talk about it? There is a chemical shorthand, and you were already exposed to this as well. This is also reviewed. Chemists use a shorthand to indicate which elements are present in a substance, and I'm going to show you some pictures of that. So sugar, you can all remember Mary Poppins, just a spoonful. Yeah, okay. Sugar, if you wanted to build a model of it, looks something like this. It's got a chain of 6 carbons. Every carbon is attached to an oxygen. Okay. I'm sorry, one carbon is attached to, no, every carbon is attached to an oxygen. There you go. And there's a hydrogen off of each carbon, and there's a hydrogen off of each oxygen. And so that's the model of it. If you were to build a model, it would look like this. But we use letters to represent atoms and elements. And so this same thing is represented here. C's for carbons, O's for oxygens, H's for hydrogens. So this is one way of representing sugar. You could say, look, there's these 6 C's. All of them are attached to an oxygen, and then there's a hydrogen on each other one. Okay? And you could draw it that way. Or you could just worry about how many of each thing there is. So we use these formulas. And this means sugar too, C6H12O6. Because if you look back here, 6 carbons, 6 oxygens, 1, 2, 3, 4, 5, 6, 12 hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So C6H12O6. This is a shorthand called a chemical formula that scientists use to help us understand what's in there. Okay? Any questions about how to read this? Do you understand that this number tells you how many of the things are right there? How many of those things there are? Yes, sir?
How do you decide which letter to use first?
Okay. When we get to, yeah, it'll be down the road a bit in the progress, but these more positive sort of elements we tend to write first, and the more negative-y sorts of ones we tend to write later, and how you tell which one is which is down the road for you. So tomorrow, if I were to give you a structure and you were to write them not in this order, that wouldn't be a problem. You don't necessarily know why they're in that order. But you do need to see that there are 6 carbons, 12 hydrogens, and 6 oxygens that make up sugar. Okay. Any other questions? Alrighty. So yeah, just to reiterate, letters tell you which atoms there are, and the numbers tell you how many there are. And we tend to use, as much as possible, a letter that makes sense for the element, like carbon is cut, right? So we use C. But then there are some where they use the Latin name, and congratulations, you all know Latin, so that won't be a problem. Where like lead is not lead spelled the same way in Latin. It's molybdenum. And so they use PB for that one. And you know, in being an English speaker, I know you don't think of PB as lead, but that's because they borrowed the Latin name, because we already had L for other things. Okay, so sometimes it's English, it's usually Latin. You'll get to know them. It'll be okay. Okay, go ahead and write that down and give you a moment to do so. Oh no, that's not what I wanted. Sorry. Okay, so we talked about atoms are the smallest unit of an element of a pure substance. Molecules are the smallest unit of a compound, where you have multiple elements bound together. But there's another situation where you have lots of things in this bucket, but they're not necessarily chemically bound to one another, right? And so the name of that is a mixture. So we are currently all in this big room, but we're not bound to one another. So we're just kind of like a mixture. We're tossed in here, we're sitting next to each other, okay? There's lots of better examples of mixture than that. But if you look at a mixture and you only see one thing, one phase is the word. It looks all uniform to your eye. You don't see chunks and you don't see layers, right? It all looks like one thing. We call that a homogeneous mixture, okay? So the idea there, genus, genus means nature, and homo, you already know what that means. That means same. Oops, that's a really cool circle. That means same. So homogeneous is the same nature. As you look at the mixture, it all looks like it's all one big friendly thing, okay? And again, heterogeneous, it's, wow, my goodness, this board is all wonky. Okay, well, I will stop using my pen. Genus, again, for nature. Hetero means different, so this is multiple natures or different nature. So several examples of that. Let me get rid of these funky yellow dots and decide where it is. Okay, so let's get some pictures. Here we have two like artists' renderings of mixtures, and in both of them, these would both be homogeneous mixtures, because here, whatever these red things are, they're totally surrounding all of the big white, the big yellow balls, and they're just, it's all mixed up. It's uniform. If you grab it anywhere, you're going to get red stuff and yellow stuff, and it's all going to be pretty much the same, okay? This one, same idea, just larger molecules. This yellow stuff is dissolved in the green stuff. The green stuff is surrounding it everywhere. This could be sugar and water, or salt and water, or oxygen and a liquid. But you've got something dissolved in something else, and this is homogeneous. It's all spread out and uniform. This is not homogeneous. This is a heterogeneous mixture. So this picture of peas, various different colors of peas, makes me want to pour some boiled water on there and add a little salt, because that looks yummy. But you can see chunks. You can see not uniform, right? If I were to grab right here, I'd have lots of green and yellow, but not much red. But if I were to grab right here, then I get a lot more red. And so it's not evenly spread out. It's not uniform. You see chunks, you see pieces. That's a heterogeneous mixture, okay? Chocolate cake batter, one of my favorite things in the universe. This is a homogeneous mixture. It's all uniform and happy. And wherever you go, you find the same uniform happiness. Nothing worse than cutting into a chocolate cake and having a big pocket of powder. Ugh. This is smooth and uniform, right? Homogeneous mixture. These are other examples of mixtures. Here we have sugar water and salt water, both of which are homogeneous mixtures. You can't see the sugar or the salt in there. It's all dissolved. It's all one thing. It looks clear. That's a good example sometimes of a good homogeneous mixture. You don't see any chunks or particles. But sand and water, you might shake it up and for a split second it looks uniform, but give it just a moment of time and it's going to settle out. And you'll see layers and you'll see chunks and you'll see different things in there. So this is a heterogeneous mixture. Okay? Tap water is a mixture. Pure distilled water would be a compound. It's all the same. Here, tap water, there's water molecules and there's minerals and there's a little bit of chlorine and there's probably some bacteria and all kinds of stuff in there. So tap water is a mixture. It would be a homogeneous mixture though, because you don't see layers and chunks in your tap water. If you do, you need to call the utility and tell them to fix that. It's all well dissolved in there. Okay. Another example of a homogeneous mixture, this is just nutrient agar being mixed up, and it is all blended and uniform. You see one thing, okay? Cool. Write those down for me. Okay, so as we're talking about molecules and mixtures and all those kinds of things, we're talking about taking different things and putting them together and making something else. And you're going to be doing chemical reactions later this week in a lab, and you'll be doing chemical reactions for a long time. That's kind of what chemistry is all about. So when we do changes to things, we want to know what kind of change did I do? Did I just heat something up, or did I change its color, or did I change its bonds, or did I cut it in half? Some changes do not affect the chemical makeup of a substance. So if I take water and I boil the water, it was water before, and now it's water vapor. It's still water. The bonds didn't change. It's still 2 hydrogens to every 1 oxygen, right? It's still water. It's just hotter water now, okay? And so sometimes the changes that we do don't affect the chemistry, and those would be physical changes. Chemical changes, however, do affect the chemistry. They change the chemical makeup of a substance. So if I were to take, let's say, well, the classic one is baking soda and vinegar, right? That's the one you guys have all done in your kitchen when you were 6 years old. You take baking soda and vinegar and you mix it together and it fizzes all over the place. And that's because you're taking some atoms from the sodium bicarbonate molecule and some atoms from the acetic acid, and they switch places. And what you wind up with is no longer a white powder and a clear liquid, but you wind up with a gas and some salt water. And so the gas comes bubbling out. It's a really cool thing to see. That's a chemical change because you changed the bonds. Different things are joined to different things. So when I heat water up, that's a physical change. If I cut a stick of butter in half, that's a physical change. If I, lots of examples of things that don't change chemical bonds. But anytime a chemical reaction happens, you had a chemical change. You've changed the chemical nature of the substance. Oftentimes, you can tell that there's been a chemical change because the temperature changes, it gets hotter or colder. Maybe some gas comes off of it, maybe it changes color. Maybe it makes noise. Okay, these are things that indicate that there's been a chemical change. No matter what kind of change you do, though, you don't get to create or destroy matter. You're not God. Only God gets to create or destroy matter. When we do things in chemistry class, the same amount of stuff will go into a reaction as comes out of a reaction. Now, it might not weigh the same because maybe it gave off some gas, and so the stuff that used to be a gas, or that is now a gas, used to be inside. Sometimes the weight changes. Sometimes it's hard to see all the matter and where it goes. But if you're careful, no matter is ever created or destroyed in a chemical reaction. No matter is actually created or destroyed even in nuclear reactions. It just changes form. So there's this thing called the law of the conservation of matter. Matter doesn't go away, and matter doesn't poof into existence, at least not since day one. Okay? At that point, obviously, it did. Energy, this is the last idea here. Energy is the friend of matter. When we talk about the fundamental nature of the universe, we have to talk about matter, and then we have to talk about energy. Stuff and what stuff can do, or stuff and the ability to make this stuff work. Okay? energy is the ability to do work. And so there's lots of forms of energy. Your book will go through several different forms of energy. And it's important that you can name some of them, especially the ones that apply to chemistry. So kinetic energy, the energy of motion; thermal energy, the energy of heat. Some of these energy forms will be much more important to you next year in physics, like potential energy or mechanical energy. Chemical energy is another one. Radiant energy or radioactive energy. Lots of forms of energy. And just like matter can't be destroyed or created, neither can energy. So, you know, Kalena is sitting there right now taking notes, and it takes energy for her to pay attention and to move her hand, and her brain is working, and all of that takes calories, right? Her body's energy unit that we study is calories. And those calories didn't just poof into existence in her body. She had some food. And so you guys just had lunch not too long ago. And Kalena, what did you have for lunch? A salad. So the complex carbohydrates in her salad are being transformed into usable energy that's being spent right now in her brain and in her hand and in her sensory organs and in her face, because she's making weird faces at me. So the energy, though, didn't come into being. It just changed forms from a chemical bond to her moving and thinking and giving off heat. Okay? So energy changes forms. Energy is never created or destroyed. That's the first law of thermodynamics. You've learned a little bit of physics today. Okay? So in the lab activity that I'm going to ask you to do, you're going to be mixing stuff together, and some of it gets hot, and some of it gets cold, and some of it gives off, you know, smoke or something like that. And all of those things take energy, but the energy wasn't created in the beaker. The energy changed forms from something else into its current state. Okay? So matter is not created or destroyed. Energy is not created or destroyed. And then we had some various vocabulary words that we used for states of matter and those sorts of things. Any questions? This is all review. You've had all of this in physical science before.